Hello, everyone, and welcome back to your channel of Basic Engineering, where I will go over the method of section of analyzing trusses. So, the method of sections, I have here a couple of examples. As the name suggests, we are going to take the truss and cut it into two separate pieces. Like you see here, this red section. Here in this problem, they ask us to find the force in members Kj, Dk, and Cd. If there are no more than three of them, you can cut through them and separate the truss into two pieces. Okay, listen carefully here. In the beginning, I'm going to look at this truss as a rigid body. Okay? Like we did before. So I can find the reactions at the supports and everything. And then I'm going to cut and separate this into two trusses. Notice that in this case, the left-hand side is smaller than the right-hand side. It really doesn't make much difference, but I am going just to draw the left-hand side. You see here you have like a triangle like that. So I have L, CL. Again, it's not, as I said, not drawn to scale. So I have, this is point A. Remember, that's a pin. So we have A sub X and A sub Y. This is point B, this is point C, this is point L. But I cut the other three members. And when you cut a member, you are exposing its internal forces. Let's assume for the sake of argument again as these three forces are tensile forces, so the forces are going away from the pin. I have two equal and opposite forces, but one of them is connected to the right-hand side of the truss and the other to the left-hand side. And since I'm analyzing the left-hand side, I'm going to see just one arrow. I'm exposing the internal forces. This is force CD. This is force K, JK, or K. We call it KJ, but we prefer to write it in alphabetical form. So JK. Oh, I'm sorry. I'm sorry. We have, no. I didn't realize it's another bay. Okay, so let's draw CK first. So this is K. And then I have an unknown force that is called JK. And a force in member KD. And this is it's not, it wasn't drawn to scale, but I'm going to do it parallel to that. DK. Notice that DK and CD intersect at point D that is outside, but I know that they intersect there. Also, this load of 40 kilonewton is not attached to my part of the truss. I only have two forces, a 20 kilonewton at B and a 30 kilonewton at C. And this part is a rigid body. It's not a particle, of course, because I don't have all the forces intersecting at a point. So in the beginning, I will draw the free body diagram of the overall truss. It's going to be a long time, so I'm not going to do it since we need time to do the next problem. So I will assume that I redrew it I took away the supports and I have here AX, AY, and GY. And I'm going to say, well, from the summation of the forces in the X direction equals 0, AX equals 0. There is no external forces in the X direction, so AX must be 0. It's not resisting anything. So in fact, I could have just deleted that, erased that, and I got this piece. In fact, after that, I'm going to take the moment about point G. Why point G? Because I'm not interested in GY. It's not attached to my truss or my portion of the truss. So I'm going to say take the moment, summation of the moment about point G, and counterclockwise is positive, and equate that to 0. So when you take the moment about G, you have the 40 kilonewton rotating counterclockwise. So that's positive times 3, 3, 3 times 9 plus 30 times 12 plus 20 times 15. And the AY is rotating counterclockwise, 18 AY equals 0. So you get 18 AY equals 360 plus 360 plus 300, right? 360 plus 360 is 720, plus 300 is 1020 Newton. So AY 40 times 9 plus 30 times 12 plus 20 times 15, and then you divide by 18, you get 56 and 2/3. Positive meaning going up. So now this guy is 56 and 2/3 kilonewton. Kilonewton, I wrote Newton. Okay, now that we have done that, we see that we have now a new free body diagram. And the way I want you to think about it is as follows. First of all, you see, I have three equations of equilibrium. Notice that the three equations of equilibrium, they don't have to be as unfortunately many think. Summation of the forces in the X equals 0, summation of the forces in the Y equals 0, and summation of the moment about a point equals 0. No. You can use three moment equation. I can take the moment about three different points, or about two different points with summation of the forces in the X, or 2 points and summation of the forces in the Y. I would have at least to have one moment equation because I only have summation of the forces in the X and Y, so I will have to use the moments. I can use the moment once, I can use the moment twice, I can use the moment 3 times. So how do I going to think about that? If you have two parallel forces, like in our case, I have two forces parallel to the X, then definitely use summation of the forces in the Y direction. Why? Because these two guys don't have a Y component. You can solve for decay right away. If I had two vertical forces and the third one is inclined, I take the sum of the forces in the X because, again, I can solve. If I don't have neither two parallel to the X nor two parallel to the Y, I can, meaning all three forces, each pair of them intersect at a point. If they intersect at a point, take the moment about that point. How could it be any easier? Here, I have two forces parallel to the X. So definitely without thinking, I'm going to say summation of the forces in the Y direction equals 0. Let's look at the forces in the Y. I have 56 and 2/3 going up, minus 20 going down, minus 30 going down, minus dk, the vertical component of dk. If you look here, you will see again, this is 3, 4, 5. So the slope here, horizontal is 3, vertical is 4, and this is 5. So the vertical is minus 4 fifth of dk equals 0. So really I get, this is 50, so I get 6 and 2/3 times 5 over 4. Let's do that. So I have this. I'm going to subtract 50 from it. Notice when I move this to the other side, it becomes positive, and then multiply by 5 over 4. And that gives me the force in dk is 8.3 kilonewton positive, meaning I was assuming it's tension, and it is really tension. See how easy now it becomes? So what I'm saying is, remember last time I told you it's up to you to decide which method is easier for you. If I had asked you to find the forces in these two members, I definitely will use the method of joints. I will find the reaction and then take some of the forces in the X and the Y. But suppose you use the method of joints here. You would solve for these two forces and then come here to solve for these two forces and then go up there to solve for these two forces, and then you solve for this force and that force, and then you will be able to solve for these. So how many members, the unneeded member forces you had to find until you reach these two joints? A lot. So in this case, definitely, if the forces are somewhere in the middle of the truss, and these are the only required members, I would use the method of sections. If these were very close to the supports, probably the method of joints would. In fact, if you come to think about it, if I take if I take a section here, I have separated the joint A from the rest. So I'm using still the method of section. And that's what I told you 2 sessions ago. All the methods are methods of sections. But sometimes I separate the truss into two things, a whole truss and a joint. We call that the method of joints. Or into two separate trusses, that's the method of sections. So it's just like a technicality here, but we always have to cut, right? There is no other way. Now I found dk. Someone would say, okay, can I use summation of the forces in the X or no, you can't. Why? Because if I take the summation of the forces in the X, I have one unknown and I have two other forces, meaning I have to separate this joint, and I can't. However, I see that these two members intersect at K, so I will take the moment about K. I can write summation of the moment about K equals 0. Counterclockwise is positive. And these two members intersect at D. Even D is not part of my truss. Doesn't matter. They intersect at D, so I will take the moment about D equated to 0. And these are the three equations I need to use. Two horizontal members, I take some of the forces in the Y. Two members intersect at K, take the moment about K. Two intersect at D, I take the moment about D. If these two were not parallel, they will eventually meet at a point. I would have taken the moment about that point. It's that simple. It is really that simple. Now let's take the moment about K. Notice about K, these two forces already intersect at K, so I don't care about them. This force, I assumed its tension, it's rotating counterclockwise, and the height here, we didn't write, so this is not a complete free body diagram. You should have noticed that. I did not, but you should have noticed it. This is 4 meters, and these are 3 meters each. It's not drawn to scale, as I said, but AB is 3, BC is 3, and CD is 3. These were missing. Okay, so when I take the moment about K, notice these intact members They have two forces equal and parallel. They cancel each other. I don't care about them. CD is rotating counterclockwise, so that's positive, multiplied by 4. So 4CD is the moment of this force. The 30 kilonewton passes through K, so it doesn't produce moment about K. What produce moment about K is the 20 that goes counterclockwise, so plus 20 times 3. And the AY that goes clockwise, so minus 56 and 2/3 times 6, right? The perpendicular distance here is 3 and 3, meaning times 6, and that equals 0. So CD becomes, you can use the calculator, this is, you take this minus that, and then you divide by 4. So 56 and 2/3 times 6 minus 60, 20 times 3, divided by 4. And that gives me 70 kilonewton. And again, I got positive, meaning I drew it correctly. It's also tension. And since this is tension, the top one would be compression for sure. Okay, so I already found now these two forces. As I said, the last equation, since these two members intersect at D, I'm going to take the moment about D. So I have JK rotating clockwise. The 30 now produces a counterclockwise moment about D. The 20 is producing a counterclockwise moment about D, and the AY still produce a negative or clockwise moment about D. So let's write everything. JK times 4. I'm sorry, we are taking the moment about D. So it's clockwise. So negative 4 JK. These two intersect here. Plus 30 times 3. Plus 20 times 6. Minus AY times 9. And that equals 0. Do you see that? Again, if you take the moment here, these two forces intersect at D, so they don't produce moment. What are the arrows that you see? I see JK clockwise, meaning negative 4 JK. Positive counterclockwise, 3 times 30. Positive 20 times 6. Negative 56 2/3 times 9. That's how you take the moment about D. And again, to find JK, the ones that are negative, when you move them to the other side, they would be positive. So between parentheses, I'm going to take the 56.6 multiplied by 9, subtract 120, subtract 90, and then close the parentheses and divide by negative 4, because I moved this to the other side as positive, so that remains here as negative 75 kilonewton, which means 75 kilonewton compression. And I found the force in all three members that I needed by using only 4 equations. Summation of the moment about G to find AY. In fact, I used summation of the forces in the X, but AX was 0, we knew that. And then did that. Okay, so that's the first example. Let's look at the second example. It's also very easy. We have a truss here, and they wanted the forces in BG, not the BGs, just BG and FG. Can someone tell me after I use the overall equilibrium, what am I going to do? Where I'm going to take my section? Again, I'm just saving time. I'm not going to redraw the whole truss, but that's what you need to do if you are going to draw the free body diagram. And I said, because really the sessions, I don't want them to be that lengthy, I'm going to assume I redrew it, and instead of the support, I made a X and AY. And by inspection, we know that AX equals 0. There is nothing horizontal. There is no horizontal forces in the whole truss like the previous example. So AX equals 0. That's what we can start doing, and DY. Now, my question to you, how are we going to cut this truss? If I want this member and that member, then definitely I'm going to cut it like that, right? Notice, when I cut through that, I have two horizontal members, so I know that I will be taking the sum of the forces in the Y to find the force in the vertical member. I also see that these two intersect at G and these two intersect at B. So now I know my three equations of equilibrium. I'm going to take summation of the forces in the Y of the left-hand side, take the moment about G, take the moment about B, and I'm done. That's, you have to develop the strategy. But in the beginning, I will do like the previous problem. I'm going to say the summation of the forces in the x equals 0, AX equals 0. So this thing is 0. And because the left-hand side is smaller than the right-hand side, by the way, you can use either. But since the left-hand side is easier, I'm going to take the moment about D to find AY. Summation of the moment about point D, counterclockwise is positive, should equal 0 for equilibrium. When I take the moment here, 800 times 10 is positive, plus the 600 times 18, 10 and 4 and 4 is also positive, but the AY is rotating clockwise, and that whole distance is 10, 14, 28 equals 0. And then I solve for AY, which would be a positive value, right? So I'm going to add these two and divide them by 28 because I can delete the 0 and say this equals that. So 8,000, which is the 800 times 10, plus 600 times 18 divided by 28 is 671.429 pounds going up. 671 and 3/7. Okay, having found AY, now I don't need anything else. In fact, without thinking, I know that the force in BG is 671.43. Let's see why is that. The left-hand side look interesting, as you will see. Here is A, and here is AY, which is the 671.43. And then I have a member AG, and member AG, this is 10, this is 10, so that's 45 degrees, right? And this is point G. I cut here, so I exposed force GE, not General Electric, or EG, should have written that EG. Oh, AB is already cut. So I have a force here. AB. And I have a force here, BG. Very interesting part of the truss is only one member, only one intact member, and three cut forces. And this point right here is B, and it's outside the truss. I just cut like that. See how it looks? In fact, I'm going to show you something. I'm only going to show my y-axis. Of course, you understand why I did that. I did it to tease the grader. Say, where is your x? Well, I never used it. I can say, this is my x. I can do whatever. It's you don't have to ask me that. If you see me writing right here for this free body diagram, not for that free body diagram of the left hand side of the truss, if you see me use summation of the forces in the x equals zero, then you deduct points from me because I didn't tell you where is x. What do I mean by x? But I won't. Remember, we have two horizontal forces. So I'm going to start by saying summation of the forces in the y equals zero. I have 671.43 kilonewton going up minus BG going down equals zero. So the force in BG is 671.43 kilonewton positive, meaning I drew it correctly. I just drew it, but I know that one of those would be wrong, but it's going away from the pin, it's tension. So I write tension. I write tension not because I got positive. I wrote tension because I assumed it's tension and I got a positive answer. Like before, I have to take the moment about G and about B, right? I cannot use summation of the forces in the X because that won't give me anything. It will tell me that GE plus AB equals zero. That's why I know one of them has to be positive and the other has to be negative. One of them is tension, the other would be compression. So let's say I'm taking the moment about point B. This is positive and equated to zero. I only have two forces producing moment about B. The GE times the height, and the height here, we said it's 45 degrees, meaning it really, later I will show you if we have time. Some other day, I will show you that the dimensions in a truss are irrelevant in your solution. What? If you give me the angles between every member and the loads, I can find the force in each member, even if you don't tell me this is 10 and this is 10. If you only give me the angles, it's the same thing. Okay, and that's how I use, for example, to analyze a big truss through a software, even simple software, let's say in Excel, I will create, in this case, 1, 2, 3, 4, 5, 6, 7, 14 equations in 14 unknowns, and invert the matrix and let Excel do it, or do it on my calculator. In this case, I will only enter angles. And maybe if we have time, I will take one of these trusses or some other truss, write it down as equations and show you how you can do it, or you check your answer using either a calculator or maybe Microsoft Excel or any other spreadsheet. You don't have to go to a sophisticated software, which you can, of course, but I'm saying if you don't have these software, you can simply um, use a spreadsheet. Now, if I take the moment about B, these two forces intersect at B, so I only have GE and the force. The reaction is going counterclockwise, so 671.43 times 10. And the GE is also going clockwise, so minus 10 GE equals 0. I can simplify by dividing the equation by 10, and I get GE equals negative 671.43 kilonewton, meaning it's 671.43 kilonewton compression. I assumed it's tension, but it turns negative, meaning it's compression. Now, because I already found G, I can use the sum of the forces in the X equals 0, because they are the only two forces. And you can see that AB would be the opposite of G. If this is compression, AB is tension. Or, since we mentioned moments, meaning here we have two ways to do it. I could have said summation of the forces in the X equals 0, GE, but GE was compression, so negative GE plus AB equals 0, so AB equals GE, right? Or I can take, since I mentioned that, I'm going to take the moment about G, and you will see it's the same thing exactly because we will be multiplying by tens. If I take the moment about G, okay, you see that these two forces intersect at G. I have the 671.43 times 10 is negative, rotating clockwise about G. And the AB is counterclockwise, so plus, and the perpendicular distance is 10 AB equals 0. Again, simplifying by 10, you get AB equals 671.43 kilonewton, positive meaning tension, because we assumed it's tension. We assumed it's going out of the joint, and it is going out of the joint, and that's basically it. So now we solve these two examples. We understood the difference between the method of joints and the method of sections, and it's up to you to decide if it's if you are asked to find, some the force in some members away from the joints, method of section is easier. Close to the joints, probably the method of joints would be easier. I think that concludes our work with matrices. I said matrices because I told you we can solve it with matrices. Maybe in the future, I will try to show you how to do that. But we concluded the topic of trusses with the zero force trusses, method of joints, method of sections. And next time we'll move to frames. So maybe tomorrow or something, I will start showing you how to analyze a frame. Thanks for your time and hope to see you soon. Bye for now.